you need to determine the minimum beam width for the section, and everybody might have a different answer, but we assume you will take that beam width you determined as a section dimension, carry it out to do the calculation for design strength, moment capacity for the last problem. Okay, so let me say this again. You will come up with a beam width by your own calculation. Just use that value for your section dimension, proceed to calculate your flexure strength calculations. Okay, so everybody might have a different answer depending on the beam width you select, but that's the expected process. Okay, if you still have a question, you can stay behind and discuss with me if you need it. Okay, so that's for homework number 3. Okay, number 3. Now homework number 4 will be uploaded. We will talk about finish it today. And we only have one section that haven't been covered, is unknown section for singular reinforced design. We'll talk about that on Monday, but you shall be able to do the first 2 problems of the homework number 4. Okay, the first 2 problems of homework number 4. Okay, all right, so let's just carry on with our lectures. Okay, so let me share my screen. So we're going to continue to talk about doubly reinforced beam section design, okay? So this is the design problem we have. We have a simply supported condition, 20 feet from A to B, dead load 1.7 kips per foot, live load 0.8 kips per foot, concrete strength at prime C4 KSI, and yielding strength of 60 KSI, grade 60, okay? We have a number 4 stirrups, 1.5 inch of concrete cover, okay? And you can find this from ACI 20.5.1.3, okay? And soft weight is already included, so you don't have to do the calculation. And beam section was restricted to be up to 14 inch and a ratio of 1.0, okay? So that means the section is given, okay? So I have so much detailed calculation done already, and these are the distributed load, and we come up with a design load, or more like an applied load, 166 kip foot. And we try to design it first with singular reinforced conditions. Okay, how to do so? We assume the beam is under tension controlled. Okay, so we introduce this parameter rho TC. That means the reinforcement limit for tension controlled case. Okay, and with that assumption, we carried out the design moment calculation, find out that the VMN is lower than the desired moment, which is 166 kip foot. That just simply means the section cannot be designed as a singular reinforced section. Basically, we don't have enough real estate to put more bars into the section, okay? So that's not gonna happen, So with that, let's continue and talk about how we're going to design doubly reinforced the section to satisfy that requirement, okay? So let me carry on, and next step number 4, different color, is to compare or find out additional moment resistance needed. Okay. So the story goes like this. I have a nominal moment capacity MN from singular reinforced case. Let me call it TC. Okay, and I convert everything back to kips inch just to be easier for me. So 1,683 kips inch, okay, which is smaller than the required, which is 166. But that's in kip foot. That approximately 2,213 kips inch. Okay, smaller than that. So that means I need additional moment. I need additional moment resistance. So simply by subtraction, I can find out I need actually an additional moment. I call it MN steel to steel, and I'll explain why, okay? That equal to the required moment capacity minus the provided TC, okay? So plug in the numbers, and this is 2213 minus 1683 kips inch, okay? And I have a 530 kips inch. That means if I provide this reinforcement area in it, okay? And what is that configuration right now, right? So given that condition, I have a section. Let me use blue color. I have a section designed for singular reinforced case already, okay? And I say I have now 2 bars here, okay? 2 bars here. I don't know how many bars exactly, just a representation. But I know the current configuration is the tension AS, right? Tensile reinforcement area AS per calculation is 2.9 inch, okay? 2.9 inch squared, so 2.9 inch squared, okay? And I also know that in the strain diagram, let me draw it a little bit differently here. And I know that from strain diagram, right now, currently, the condition I have is the compressive zone C here, and equal to beta 1 A, and C here equal to beta 1, A divided by beta 1, A divided by beta 1, and A from previous calculation is 3.66 inch, okay? So this is 3.66 inch. And my concrete is 4,000 PSI. My concrete is 4,000 PSI. Tyler. Yeah. So what is beta 1 for my concrete 4,000 PSI?
It should be 0.85.
Exactly. Thanks. That's a good answer. So that's my beta 1. And I got my compressive zone C from the current design. I have about 4.3 inch. Okay. So let me just write it out in terms of inch. Not to confuse you. So that's my current design, okay? And I know my current design, concrete has a 0.003, okay? And this is my steel right here. Okay, that's my steel right there, okay? Now, the problem we have is the design is inadequate. A design is inadequate. That means I need additional moment. So where can I find this additional moment, right? So I'm just gonna assume I'm going to put some bars here in the compressive zone. I'm going to put the bars here in the compressive zone. I don't know how much, but let's say AS prime. Okay, and I'm going to add a moment to it. Right? So the additional moment caused by this compressive reinforcement is Mn steel to steel equal to AS prime. That's the compressive area of steel. Then stress in the compressive reinforcement. Okay, and that's the compression force by the steel, right? CS. Okay, and mass by the lead bar, which is the distance between the top bar and bottom bar. Okay, now given the concrete cover for the top bar is D prime, okay, and the depth for the bottom bar is D, the distance is basically D minus D prime. D minus D prime.
Question.
Yes.
Why do you put the bars up top and not maybe add a bar to your row? So instead of 2 bars, maybe add 3 bars.
Oh yeah. So I just said in the previous lecture, we can add more bars here, right? But the problem,
yeah, okay.
We only have 14 inches, so we just don't have so much of real estate. Means spacing-wise does not accommodate easily with us.
Gotcha.
Yeah. So that's why we said previously, this doubly reinforced section, particularly good for a stocky section. That means like a wide beam section, not so deep. Okay. All right. Okay. All right. So we're gonna have this additional moment resistance provided from compressive reinforcement. Okay. So let's just do a quick check, right? I need to know. Right now, I already know. I know this required additional moment is 530 kips inch. Okay, all I need to find out is this AS prime area still. Okay, excuse me for 1 second. There's noise. Let me just close the door real quick. Okay, sorry about that. So I just need to find out my required steel AS, right? So the question is, what is AS prime? Okay, so I already know the D minus D prime. That's given. So the only thing that need to be determined is Fs prime. Fs prime. Okay, so what is Fs prime? Let's do a quick check. Fs prime equal to ES, Young's modulus of the steel, multiplied by strain in the steel and the compressive steel, right? Epsilon S, which means if I use red color right here, which you can see is right here. Okay, epsilon S prime. Okay, and I can calculate that using the equation, right? So ES multiplied by 0.003, which is epsilon Cu, multiplied by C, compressive zone, minus D prime divided by C. Okay, then bring the number here. So this is 29,000 KSI. Okay, and this is 0.003, and C is 4.3 minus D prime 2.5. Okay, and then inches divided by 4.3 inches. Okay, I got this number to be a 36.8 KSI. Okay, so now I can go back and calculate AS prime equal to MN steel to steel. That's additional resistance I get from compressive reinforcement divided by Fs prime D minus D prime. Okay, so that gives me 530 kips inch divided by 36.8 KSI and D, which is 11.5 minus 2.5. Okay, and I found this to be 1.6 inch squared. All right, so by doing the difference, I know I need additional compressive reinforcement, and this much, okay, this much to complete my design, Okay, so now I know the compressive reinforcement I need, and I know the tensile reinforcement I need. So I'm going to start doing the design. Okay, so step number 6, select bars. Okay, so now I know AS prime equal to 1.6 inch squared. Okay, from previous case AS, right? AS tension equal to 2.9 inch squared. Okay, so naturally, right? Naturally, I just add them up together, right? Add 2 together, right? Now I have the total required reinforcement, right? But not so fast. Something changes. What changes? Now, take a look at the previous section, right? I put bars in, right? Additional bars in. That means I occupy the concrete was originally there. I'm going to say this again. So I take the bars and put them in. So I replace the concrete that was there before, isn't it? So I have to give it back. Right? So how do I give it back? This is how, right? So I have to say now AS, okay, due to the compressive zone, let me just call it AS2, okay, equal to what? AS prime and multiplied by Fs prime divided by Fy. Okay, and I convert that into steel, right? So that is 1.6 inch squared multiplied by 36.8 KSI divided by 60 KSI. Okay, and I got 1 inch squared. Okay, now this is to account loss to concrete. Okay, this is to account loss to concrete. All right, so now with this, I will say now the total tension steel, AS total, equal to the AS1 or AS previously plus AS2. So that is 2.9 inch squared plus 1.0 inch squared. And this gave me a 3.9 inch squared. And this is a tensile reinforcement. Okay, so this is tensile reinforcement. Okay, and now still AS prime, which is compression, that is 1.6 inch squared. And this is compressive reinforcement. Okay, compressive reinforcement. Okay, now I can select bars, right? I'm simply going to select 2 number 9 bars for AS prime. Okay, so that have 2 inch squared. Okay, and 4 number 9 bars for AS. Okay, and that gives me 4 inch square. So this is provided reinforcement.
Bob,
Yep,
I have a question.
go ahead.
So why did we need to add that AS2 to the tensile reinforcement?
Right, think about it, right? So originally, I had concrete here on the top, right? Before, there were concrete, right? Right? Now I put compressive reinforcement in it. Steel, right? So steel
Okay.
is stiffer than concrete, isn't it?
Steel is what? I'm sorry?
Stiffer, harder, rigid, right?
Yes.
So you're adding more compression to your member, isn't it?
Oh, I understand.
Right? So the original steel, the singular reinforced case we designed for, that steel take care of all the compression from the concrete. Now you're putting steel as a compressive reinforcement. The added compression need to be balanced. So you add tensile reinforcement corresponding to that balance.
Okay, thank you.
Sure, no problem. Okay. Now this, yeah.
Why did you? So I understand why you selected 2 number 9s for AS prime, because that gives us an extra 2 square inches. Why'd you select 4 number 9s, and not just 3 number 9s?
Well, this is 3.9 inch square, right? That's
okay, yep, okay.
Yeah, you're right. I mean, yes, just select higher than that, right? I mean, if it was previous case 2.9, then we'll just read 3 bars, right? Okay, good. All right, so that is the current situation. So look at the bars here, okay? And I want to say this is one way to solve it, okay? There are several ways to approach that thing. I find this way just easier for me, okay? So I'm going to share with you guys, and we can talk about other ways as well in the next lecture, okay? But today, let's focus on using this approach, all right? So now I'm looking at the section here. Looking at the section here, okay? I have 4 AS, which is 2 row, all right? And 2 AS prime. Okay, still very crowded, still very crowded. Okay, still very crowded. Barely fit. By yourself, barely fit. Okay, barely fit. All right, so that is my current section. That is my current section. But keep in mind that I've changed my section. I've changed my section from single reinforced to double reinforced. Okay, so I need to know what is my capacity of the beam right now, and to make sure that is bigger than the applied. That is bigger than applied. So step number 7, check BMN. Okay, so I'm gonna go ahead and assume C, compressive zone, remain the same. Why? Well, I think I'm pretty good in providing reinforcement that is very close to the design, right? Remember all these calculations coming from the compressive zone that is shown here, which is 4.3 inches, right? FS, 36.8 KSI, all coming from here. So as long as I provide reinforcement that close to these values, I'm gonna say, I assume C remains constant, did not change, okay? Then you can proceed with the calculation, and you find out, I'm just gonna save us a little bit of time. Remember the table here? Remember analysis table? C is different values, and epsilon S prime, remember? AS prime, FS prime, okay? And concrete, 0.85 prime C, beta 1, 0.85 at prime C, beta 1, C, B, concrete, remember, and steel, CS right here, and tension, ASF1, okay? And don't forget, see, I made a mistake already here. Don't forget your substrate. CS prime, FS prime, and move this one here. I need more to work with. Minus 0.85 AS prime. Okay, that's what I'm seeing. Okay, and that table we used before in the previous lecture, trying to iteratively make sure C equal to T, right? T equal to CC plus CS, and Mn equal to T, B minus half A, okay? And plus AS, FS, well, should I use the, this is tension T, this is, okay, so CS, D minus D prime, right? That is what we did before. That is what we did before, okay? All right, so I want to leave us a quiz, okay? This quiz is a little bit long. I want to leave us a quiz, okay? The quiz is today, here, number 4. Given a design, okay? Given a design like this, so this is 14, which is height, and the width is also 14, okay? And now I have dt equal to 11.5 inch, dt equal to 11.5 inch, okay? And right here, top bar here, let me say this is 2.5 inch, D prime, okay, 2.5 inch D prime, okay? The quiz is to find out Mn and phi, okay? Mn and phi, okay? And I can give you a solution. You need to show the full work for this one, okay? Show full work. Okay. Show full work, okay? And I can give you a hint. The phi, sorry, not phi. The final answer, phi Mn, equal to 2036 kips inch. Okay? See if you can get this number. I want to see the full work. Okay, and I'll open up a quiz, all right, for this one. Okay, all right, any questions? Are we good on this? Any questions on this? Okay, now this may take a little bit of time to digest, and we'll emphasize it again on Monday. Okay, we'll emphasize it again on Monday. Okay, so today is going to be a short lecture, unfortunately. Today is going to be a short lecture, unfortunately. But I want us to stay behind and talk about the homeworks. Okay, so let me open up the homeworks. Let me just stop sharing for a second. Open up the homework number 3. The quiz is going to be due next Thursday. Always, okay, well, this quiz is a bit different. So let me type. This is due next Thursday. Just in case I forgot, okay? So I'm going to homework number 3 open up real quick. Show you guys. Here we go. Okay, so problem number 1, concrete beam with cross section having geometry shown below, nominal compressive strength from C 4,000 psi, positive bending, okay, positive bending, grade 60, okay, so that's the conditions. What is the effective depth of section assuming all bars were number 9, right? So first step, you find the center of the group of the bars, okay, with respect to the bottom surface, okay, and use the total height, subtract that to get your depth, okay. Now, what is the strength reduction factor assuming all bars were number 9, right? What is the strength reduction factor, right? You got to do the C equal to T, find out the compressive zone, right? A, and get the actual compressive zone C, right? And get the T, which is the strain at the bottom bar here. Strain of the bottom bar here, okay? And if your strain of the bottom bar here is be smaller than 0.00207 or 0.02, that is compression control. So phi equal to 0.65. If it's larger than 0.005, tension control is 0.9. In between, you have that equation, transition, right? Now, what is the cracking moment of the section assuming all bars were number 9? So quick question here, okay? Lucas, look.
Yeah.
Hey, so how are you, buddy? You doing well?
Yeah, how are you?
All right, not too bad. So one to see here, the cracking moment of the section, assuming all bars were number 9. Do I really need a bar to calculate the cracking moment?
I don't think so.
Don't think so, right? That's the right
Yeah.
answer. So we don't need the bars to calculate the cracking moment. Just use the section, right? So if you forgot the equation, right? If you forgot the equation, simply M crack equal to MR, FR, right? That is the strength of it, I moment, right? Cross section moment, right? Some moment of inertia of the cross section, right? Right? And Y, what is Y? Is half of the height, right? So H divided by 2. Is that right? That is the cracking moment. Okay? That is the cracking moment. Okay? All right. So 1D, what is the design? What is the design? Close it out. What is the design? Flexure strength being assuming all bars number 9, right? You know how to do that. And repeat 1A, 1B, 1D, assuming all bars are number 8. Now, considering the difference, number 9, number 8, right? So if you use the number 8, you have more number of bars. You have more number of bars. So see, if you have 12 inch of width, now if you need 3 number 8 bars to have the same area of number 2, number 9, you might not be able to fit them. You might not be able to fit them, okay? So be careful on the spacing. Be careful on the spacing. All right. For homework number 2, it's a doubly reinforced case. All right, not too bad. So first question, determine nominal flexure strength and then doubly reinforced section positive bending. Okay. Before we start, where is the maximum moment? Where is the maximum moment? Adam.
Yes.
Hey, how are you, buddy?
Good. How are you?
Not bad. So where is the maximum moment of this problem? Is it at support? Is it in the middle span? Quarter span?
In the middle.
In the middle, right? So that is the maximum moment. Okay. And don't forget, all right, this is 1.2 depth plus 1.6 lat. Okay. All right. So this should be straightforward, right? Just follow the process. Okay. Now, 2B, draw the strain distribution, nominal flexure strength of the section, label the key value of strain to show the strain diagram, right? And depth and neutral axis, which is C. Okay. Verify the area reinforcement provided meets the minimum requirement. Remember the equation, 3 square root of prime C, right? Divided by Fy and BWD, or 200 square root of prime C, Fy, BWD, right? No, there's no square root of prime C, just 200, okay? All right, so 2D, if the beam is subject to uniform distributed load, okay? And service level shown above, determine whether the beam is adequate, okay? Don't forget the 1.2 plus 1.6, all right? So 3, calculate the minimum beam width for the beam shown below, all right? The clear cover to the stirrups on all sides is 2 inches. The maximum aggregate size is in concrete is 1 inch. Okay, so that is tell you the spacing. Okay.
Bob.
Yep.
The homework that I found on Canvas didn't have problem number 2 on it.
Oh, did I? Oh.
Yeah, we have a completely different homework than what you're looking at.
Yeah.
At least for 2 and 3.
Yeah, this is my old version. Let me open up my new version. I have 2 versions.
Scared me at first.
Yeah.
I was like, what the heck?
Sorry about that, guys. Yeah, I think I made a mistake there. Okay. Yeah, I have 2 versions of it. This should be it. Okay, I think I got it. Sorry. 2 versions of it. Give me the goosebump as well. Is this bad? Is this the one that you're looking at?
Yeah, that is.
All right, this is one, right? Okay. Yeah, sorry, I have 2 versions of it. We end up using the other. I forgot about it. Okay. All right. The problem number 1 is the same though. Not much difference. Okay. 2 and 3 is different. All right. So what is the effective depth of section? You need to find the center of all these group of bars and then find the effective depth. Okay. This is trivial. Now, like I said, the minimum beam width of the section. Now, once you determine the beam width, you can use table A5 to check your number. All right, your number should be close to the required number from A5, okay, by half an inch, Now, if your number is bigger than the textbook A5, okay, we need to see what's going on. But you pick the biggest number, either your solution or the table A5, the larger number dominates, and round up to integer. Okay, there's no half inch in the beam width. Okay, if it's like 12.5, make it 13, so on and so forth. Okay, now strength reduction factor, design flexure strengths, like I said, these are based on the beam width you selected. So everybody might have a different answer. All right, everybody might have a different answer. Okay, all right, repeat problem number 2, assuming the cast in place concrete beam has been set cast permanently against the ground with number 3 steroid instead of number 5. Okay, so 2 things are different from number 2. One is cast in place concrete beam permanently against the ground. That means the concrete cover changes. Concrete cover changes. Okay, should be able to find that in the table 20.5.1.3. Okay, and now the other thing, number 3 stirrups instead of number 5 stirrups. Okay, so the stirrup size reduces. When you have a stirrup size, it reduces. You have more spacing allowed, but your beam width changes. Your beam width changes. Okay, if your beam width changes, subsequently you change your stress reduction factor and design flexure stress. Okay, all right. So that's all actually for today. I have a short lecture today just because I worry about homework. So if you have any question about the homework, you're welcome to stay behind and let's discuss. Okay. If no else, we can meet on Monday again, talk about the design for not given the section, right? For for unknown section geometries. Okay. All right, guys, that's it. And let me know if you have more questions. Okay.
Thank you, Bob. Have a good day.
Yeah, you too. Thanks.
See you, Bob.
Yeah. Any other questions, guys? If you have any homework,
Yeah, I have some homework questions.
Adam, go first. Adam or?
I didn't have any.
Oh, sorry.
I'll submit him first.
Who said that?
I did, Ben.
Okay, hey, how are you?
So for the doing the part B on number 2 and I guess number 3, just ran into a little bit of confusion trying to, well, I guess starting on part A on the effective depth for the vertical spacing between the bars. Do we use the 1 inch that's given, or do we need to do the do the 1.33 times the diameter of the aggregate?
Good question. So for the vertical clear, right? What is the criterion? Do you still remember?
Yeah, it's larger of the 4/3 diameter of aggregate or 1 inch.
So which one's bigger?
The 1.33.
Like use that.
Okay.
Yeah. Don't worry about this.
Okay, because I just it showed 1 inch of the clear right there, and I just thought that you would assume that that's.
If you're already done with 1 inch, go ahead with that and see what you end up with. But
I did it with both of them, and the answers end up being super similar. So I was just wondering for exams.
No, I mean, this is kind of a trick question. We make a 1 inch clear just to remind you that the bars at least have a 1 inch clear spacing, but it is actually the aggregate side dominates.
Okay, cool. Okay, so that clears that up. And then also for the minimum width, could you kind of draw out how you would do it, but not with numbers? Because it's I tried following the example that you did in class with just the 3 bars across the bottom.
Yeah.
And I just run into some discrepancies. The bars don't sit on the side edges of the stirrup, right? They only sit on the bottom.
They're not. So I think I know where the confusion, and that's why I have a short lecture today, because I know that you guys might have troubles first time solving this type of problem. Okay, so all the complexities are in the corner. Is that right?
Yeah, exactly.
I'm gonna use blue bar, show you the stirrup. So this is the stirrup, it looks like. Can you see it?
Yep.
All right, now I have a bend. Because the corner is gonna be in terms of a circle, right? Quarter of a circle. I have a bend here. Okay, so this is the bending center, right? Center of bending. Now, when I put my bar, I'm gonna use red color, okay? The bar is gonna sit right here. So the bottom of the bar is gonna be in contact with the stirrups at here. So the center of the bar line up with the center of the bending radius. Okay, all right, so now, there are 2 times, all right, the distance between the edge of the stirrups to the center of the bending radius 2ds, and ds being the diameter of the stirrups.
Yeah, and then the distance from the edge of the bolt to the edge of the stirrup would be the 2ds minus the
That's good.
diameter of the bolt over 2, I believe. Yeah.
So this is so-called a gap. Isn't that
Okay.
right? So that's where the confusion, I think.
And that's constant throughout all the, even though the
That's
figure in the homework kind of looks like it is touching the stirrup on the left side.
Yeah.
Okay, and then this one also has 4 bars across the bottom, and instead of having like one bolt be right in the center of one bolt being the halfway point for BM, like how we did the BM over 2 and just multiplied, and like we did the width halfway and just multiplied by 2.
Yeah.
I tried doing that same thing, but I was just wondering if you could like variably like write it out and see if that matches up with what I had. Something, I'm pretty sure like you showing that made it clear. I was just confused.
Don't worry. So this spacing right here, you know how to determine that, right?
Yeah, that's the same as the vertical, but with 3 criteria. It's the diameter bolt 1 inch or the 4/3 diag.
I'm just going to call spacing as T, okay? Just for sure.
Okay, yeah.
Now, this is same, isn't it? The spacing between these 2 bars is same.
Mm-hmm.
All right. So assuming I'm going to have 4 bars, I believe that's the problem, right?
Mm-hmm. Yeah.
4 bars. Blue color right here. Okay. Now, I want to do a half beam width. Half beam width, okay? It's symmetric, right?
Yep.
So, my minimum. Okay. So that equal to, let's call this clear cover CC, okay? All right. So that's going to equal to CC plus DS stirrups, right?
Yep.
And plus
The gap.
2DS minus dB over 2, that's the gap. Okay. And plus, remember the bar, right? I still have the bar.
Yep.
dB,
The whole bar.
whole bar. And plus the spacing, right? And plus another bar,
And then half spacing.
half spacing. Okay. And then, so the B, the whole thing, equal to 2 times of this.
Gotcha. Okay, that's what I did. Cool.
Good.
Just wanted to double check that. It was a little bit confusing.
Yeah. Cool.
And then what else did I have a problem?
Mm-hmm.
Yeah, that pretty much clears up everything I was a little bit confused about.
No worries. Good deal. Anything else?
Yeah, I have a few questions.
Go ahead.
So the first one is kind of just like general homework and like exams.
Mhm.
So I emailed you about this yesterday. I don't know if you saw it or not, but so for example, if we would mess up like A for one of these problems,
Mhm.
would the entire problem then be counted wrong, or would you grade based on like the incorrect A value, but let's say we solve C and everything else after that correct? Would we get?
It's a very hard question. First of all, I don't grade the homework. I have a grader for it. But I communicated with him. I asked him to give you partial credits.
Okay.
If you did it wrong, you're really at his mercy on how much you can get in terms of partial credits. Okay.
Okay.
I'm saying that is sometimes your next step answer is kind of dependent on the previous one, isn't it?
Yeah. No, I totally get that. I guess I was just asking if there was partial credit.
Oh yeah, I told the grader that they should give you partial credit.
Okay. Cool. Okay.
Yeah. Okay. Anything else?
Yeah, I got one final last question. Whenever we're finding effective depth, or not even effective depth, just the strain T, I guess it would be called. We always use the distance to the bottom row of the bars whenever there's multiple lines.
Yes.
Always.
Yes, that's called T, by the way. Can you see the strain still?
Yeah.
That's T. So if you have 2 rows, just gonna make things up here, okay? If you have 2 rows and it's always dt.
And we always use that DT to find the fee, essentially, right?
Yes. So phi
Okay.
is always a function of dt.
So I was just talking with some students in the other section, and they were seeming to just do the like the regular T or regular D minus C, and I was like,
Sure.
we're learning that differently, and
By the book, by the code, you can check as dt, okay? That's
yeah,
the book, the code. But you think this way, ds is always smaller than dt.
except whenever there's single row.
Yeah, so ds is smaller or equal than dt, right? When they're single row, they're the same.
Yeah.
Right. So we're saying is if you use ds, your strain in the epsilon in s at the level of ds is always smaller than epsilon t.
Mm-hmm.
So if your epsilon s is 0.005, then epsilon t has to be bigger than 0.005.
Gotcha.
Right. So you're saying is if you check on epsilon s is showing that phi equals 0.9, this is also valid. However, if this is some other values, you got to be careful.
And then on those values, do you want us to round them? Because like, for example, on one like E, I got a
Which
like
value you want to round up? Which parameter you're talking about?
the epsilon T.
Epsilon t always round up in the say 0.002 something. So it's 2 effective digits at least.
Okay, because like I found one to be 0.00448,
Yeah.
and
I
I
use 3 digits in my.
gotcha. Yeah, that's I saw you do that, and I tried to follow, and then I found that being less than 0.005, so I determined it to be in transition, and the fee is you gotta use the equation to find it.
But I think you quickly find out if it's really sit on the border, it doesn't matter. You plug in the transition equation, you're gonna get something close to 0.9 anyway.
Gotcha. Okay, yeah, and that's exactly what happened. Okay, cool.
Yeah.
Thank you very much. Have a good rest of your day.
No problem. Yeah. See you later. Anything else, Tyler, Bryce? Are we good?
I'm good. Thank you.
Yeah. All right. See you later. Okay. All right.
Oh, and one last thing is when can you post these notes that we did today? Because I had some internet issues at the beginning of class, and I didn't really get to start, and then I was kind of lost and just was forced to listen and not write.
I understand. Let me do that right away. How about that?
Awesome. That would be very beneficial. So I could use this time and catch up on that.
Yeah. I think you have all the other previous notes, right?
Yeah, I got everything else. It was just today's at the start of the lecture, I was catching up on something, and then my internet lagged, and you were moved down to like part 5, and I missed 4. And
Sure. I understand. Don't worry about it. Okay. Yeah. You
awesome.
see. Yeah.
Thank you very much. Have a good rest of your day.
Thanks. Bye now.